Hey everyone, it's your Professor Andy here with a video tutorial on projectile motion. So let me go ahead and hide my video and share screen. There we go. Okay, yeah, so this is going to be a 20-minute video. There is going to be a quiz question at the end of the video, so you will need to answer and submit that to get credit for watching this assignment. Okay, so let's go ahead and get started. We are talking about projectile motion. So this is just like free fall, but in 2D now. So just like free fall, the acceleration is the acceleration due to gravity. It has magnitude 9.80 meters per second squared, and it points down. So in terms of the components of that vector, that means that AY is negative 9.8, while AX and AZ are 0. What about the equations of motion? Well, the same ones we had from before are still applicable as long as that acceleration is constant. Okay, so here we see those equations of motion in vector form. Let's just remind ourselves what all this notation means. So the position vector R has components including the x position, y position, and z position. R naught is the initial position vector whose components are the initial x position, y naught, and z naught. V naught is the initial velocity vector, whose components are v naught x, v naught y, and v naught z. And then here is where we have our acceleration vector. And then again, for projectile motion or free fall, ax and az are 0, while ay is minus g. All right, so remember, g is our magnitude of acceleration due to gravity, and that's our 9.8 meters per second squared. The time here is common to all the components of this equation. So if we write out that vector equation the long way, right, we break it into three separate equations, those equations would look like this. Except that if we're doing projectile motion, this term is gone and this term is gone. So the x, the y, and the z equations are independent. Only gravity affects the vertical motion, but all three directions are coupled in the sense that they share the same time t. So if an event like a football landing on the ground occurs in the I hat at time t, then it also occurs in the j hat at that same time t. Okay, so how do we go about solving a projectile motion problem? So the following four steps are going to pretty much work in any scenario you can imagine. So the first step is to draw a picture if you aren't already given one, and though to draw your coordinate system on the picture indicating where your origin is. You've got to have a coordinate system to be able to follow this procedure. Make sure, so then the next step is to make two columns listing all known and unknown data for the x equation of motion in one and for the y equation of motion in the other. So for example, do you know the initial x and y position, x naught and y naught? Maybe you know the final positions, x or y. For example, if the object hits the ground, that probably means y equals 0 if you put your origin at ground level. Maybe you know the initial x and y components of the velocity. Do you need to use trig to express them in terms of a given initial speed, v naught, and angle theta? And if it's a projectile motion problem, then you've got your components for your acceleration. Third step is under the data in each column, write out the equations of motion in each direction and then plug in all of your data. That will usually result in two equations and two unknowns. And so the final step is to solve that system of equations by substitution to find your target variable. All right, so let's see how this works in practice with an example. So here we have a swimmer who wants to dive off a cliff with a running start. And we want to know what must her minimum speed be so that she misses that ledge below. So she's 9 meters above the ledge, and the ledge sticks out 1.75 meters there from the edge of the cliff. So yeah, this is a very important problem for her to find how fast she needs to run and can she run that fast. Okay, so we've already got our picture. So then the other part of that first step is to choose a coordinate system. Where do we want to put our origin here? So I like to have as few minus signs as possible with respect to my positions. So from this example, I'm going to go ahead and put the origin sort of where it's already suggested here. down in the corner. So that'll be my x-axis, that'll be my y-axis. And now we're ready to go ahead and start constructing our data tables. So we're going to have x data and y data. And what are the things that go in this table? All of the things that appear in the kinematics equation. So positions, initial final, velocities, initial final, accelerations. Let's start with initial position, x naught and y naught. So based on our coordinate system here, the initial for the projectile motion problem, right, when only gravity's acting, is going to be the instant she leaves this ledge here. And so her initial x position in our coordinate system is 0, while her initial y position would be this 9.0 meters. So let's solve this problem symbolically. Let me set that to h for now, right? But h is a given. Let's go and think about initial velocities, v naught x and v naught y. So here we see the initial velocity vector indicated, and the magnitude of that, the initial speed, is our target. But we can still say something about the components in terms of that target because we've been given the direction. It's dead right. So if you've got a vector that's dead right, then its x component is its magnitude, and its y component is 0. Next, we could do accelerations. This is projectile motion. So ax is 0, ay is minus g, or minus 9.8. Whoops, let me fix that. And then what else? Well, we could talk about final positions. So she wants to clear this ledge. So at a minimum, we should set x equal to 1.75. And then when we're at that x, we're at y equals 0 in our coordinate system. Now for the second part of this problem, we're also going to want to know the speed as she hits the water. So that would be the magnitude of her final velocity. And so final x component of velocity is a target, and final y component of velocity is a target. And then we also have t as a target. And that kind of goes with both tables, so I usually put that down here. Our target for the first part of the problem is right here. Okay, so that was step 2. Now we are ready to write down our equations of motion. Now you've got several equations of motion for constant acceleration on your formula sheet. How do you know which one of those to use? That's kind of what this table's for. It's listing out all of your knowns and unknowns. And so you want to pick the equation that's going to connect your knowns and unknowns. When I look at this table, I see I know a lot about positions, and my target is an initial velocity. So that makes me think of the equation we had on the earlier slide. So the vector form of that was r equals r naught plus v naught t plus 1/2 a t squared. So let's write that out in general in x and y. So in x, that'd be x equals x naught plus v naught xt plus 1/2 ax t squared. And in y, it would be y equals y naught plus v naught yt plus 1/2 ay t squared. Now let's go ahead and plug in what we know. So starting with the x equation, we can cancel out the things that are 0, like the initial position and the acceleration term. And then this equation, plugging in the rest, becomes x equals v naught t. So we know x, but I'm going to leave that sort of as symbolic right now because I might also want to consider x's that are bigger than that absolute minimum. So let's leave this equation as it is, and let's see how the other equation develops before we sort of decide how to proceed. So plugging in on the y side, our final y is 0. And the other term that's 0 here is our initial velocity term in the y. So then we have h for our initial height, and then ay, remember, is minus g. So this term becomes minus 1/2 gt squared. Okay, so now we see that we have 2 equations, and they involve 2 unknowns, t, which we're not really interested in, and our target v naught. So let's bring it up over here two equations, two unknowns, T and V naught. So what I see is that I can solve the y equation for t in terms of knowns. And then once I have that, I can plug into the x equation to get my target. So solve the y equation for t. So let's move the term that involves t to the other side, and that gives us 1/2 gt squared equals h. And then I'll multiply through by 2, divide through by g, and take a square root, and we've got our time. So 2h over g, whole thing, square rooted. Now let's go and look at our x equation. Let's first solve that for our target v naught. So x equation tells us that v naught equals x over t. And now we can plug in this t that we found. Now, when you divide by the square root of a fraction, that's the same thing as multiplying by the square root of the flipped fraction. So I'm going to write this as x times square root g over 2h. And now we can go ahead and plug in numbers. So if we plug in the smallest possible x that clears the cliff, that is going to be exactly our target, this minimum speed that we were asked for. So v naught min is 1.75 meters times the square root of 9.8 meters per second squared over 2 times this 9.0 meters. So we see under the square root here that our meters cancel out. And then in terms of units, we have per second squared. When we square root that, that's per second. And so the total units on this answer are meters per second, which is exactly what they should be for speed. So then doing the numbers, I find 1.29 meters per second. And so that's the minimum speed she needs to clear the ledge. And so we could say she should take v naught greater than or equal to 1.29 meters per second. So remember how we were saying earlier that miles per hour is a little bit more than double a number in meters per second. So let's say that this is roughly 3 miles per hour. That's no problem at all. You can even probably walk that fast. So she can definitely clear this ledge. Okay, so let's talk about the next part. What is her speed as she hits the water? So in terms of what we're after, remember that speed is the magnitude of velocity. So our target is simply v, right? And in terms of the x and y components of that final velocity, we would use Pythagoras to get that speed. So our job now is to find those components and then plug into Pythagoras. So for the components, we need another kinematics equation. And looking at our formula sheet, right, the one that seems the most relevant would be v equals v naught plus at. So writing that in components, we have for the x component, vx equals v naught x plus axt. And we can kill the acceleration in the x, and we learned that vx is v naught x. In other words, the velocity doesn't change because there's no acceleration in the x. Now v naught x we set up here was v naught, and that was what we found, 1.29 meters per second. Meanwhile, Vy is V naught y plus Ayt. We don't have initial velocity in the y in this problem. Ay is minus g, so this is minus gt. And now we can go and we can grab that time that we found earlier, and that was square root 2h over g. And so now when I plug in numbers here, I get negative 13.3 meters per second. So now we can take these two numbers back to Pythagoras to get our speed. So this is going to be the square root of 1.29 squared plus, I'll drop the minus since we're squaring anyway, 13.3 squared. And this comes out to just a little more, 13.4 meters per second. Roughly 30 miles per hour. That's pretty fast, so you definitely don't want to belly flop this one. Okay, so that's this example. To wrap up this tutorial, I actually want to do a classic demo for you. So this demo used to be called the Hunter and Monkey. Now it's the zoologist and the monkey. So this is just a tranquilizer dart gun you're seeing here. And the idea is that the zoologist needs to tranquilize the monkey to administer some medicine. The monkey is hanging from a tree branch. Now, the monkey's been through this before, and so his plan is to release himself from the tree branch the instant the dart gun fires to try to avoid the dart. The zoologist has also been through this before, so he knows the monkey's going to do this. And the question is, knowing that the monkey will do that, where should he aim? Should he still aim dead at the monkey, like you see in this picture here, or should he aim above or below the monkey? What do you think? So the way that we're going to approach this in the demo is we're going to take dead aim at the target, and then we're going to see if we hit it, or if we go under it, like you see here, or if we, whoops, go over it, like you see here. Okay, so let me go ahead and stop share here and turn my video back on so you can see me and you can see the demo. There we go. Okay. So attached to my desk here, I've got my projectile launcher. Okay, and it's already loaded. And then over here, hanging from the ceiling, I've got my target. That black one over there. Okay, there it is. And so what we're going to do is to make sure that when the ball fires, the target releases, we've got a sensor, our photogate sensor from the lab earlier, right, that will be tripped when the ball clears the muzzle. And so when that's tripped, it'll send an electric impulse to release the target. So just to show you how that works, I'm going to go ahead and trip it once with my finger. Okay, here we go. All right. So let me go ahead and replace that, and then we'll do the demo, okay? Oh, yeah. So you might not be able to see it because it's going to happen pretty fast. Okay, so I've taped a little bit of carbon paper on top of white paper. So if the ball hits the carbon paper, it'll leave a mark on the white paper. Hopefully you can slow down the video as you're watching it too to be able to catch that strike if we hit it. Okay, so we are ready. Here we go. All right, we nailed it. Let's check. There's our mark. Okay, not too bad. Okay, so we should apparently aim right at it. So the question that I want to leave you with, and we'll do this demo again in person next week in recitation so you can check that I really was aiming right at it. But let me go ahead and share screen one more time here. Is this question. Actually, let me get to the next slide. This one. So suppose that our muzzle speed is so low that the dart reaches its apex here at point P before it even gets to the monkey, right? Here's the question. When the dart is at that apex, right, assuming the monkey's going to get hit, where's the monkey? Is he at point A, above that point, at point B, at the same height as P, or below P at C? Okay, so go ahead and answer that question on the video quiz that'll pop up here in a minute, and make sure you submit so you get credit for watching this. And we'll leave it at that. Okay, so I'm going to go ahead and stop share, and I will see you in lab.